Now that we have the initial benchmarking results, whenever we want to perform a prompt engineering, say that we are updating the prompt to improve the accuracy of the model, we have to run this benchmarking suite once again. And if you remember, the whole suite of processing 100 samples took around 17 minutes for us. Imagine we are making an update in the prompt. To find the effectiveness, we have to wait for 17 minutes to run the benchmark and find the results. To optimize this, we are going to leverage the VLLM package. The reason for choosing VLLM is not only for performing the parallel inference, but also that the VLLM makes the code changes really simple. Today, we are running this setup with Wen 2.5 vision language model. Imagine we have to extend this test for multiple different models, say PHA4 or any other new release models. In such cases, we just have to change the model name and the prompt structure of that VLLM. This makes our life really easier, and hence it makes sense for us to update this inference step with VLLM, and we can enable the parallel processing to process it much faster. Make sure to install VLLM in your system. I have already installed it and I'm skipping this step. Go ahead and load the dataset. Dataset is loaded, and this is the schema dictionary. And this, and the next step for us is to create the prompt. For this particular test, we are going to try with another simple prompt, which is you are an expert in invoice extraction, and your role is to extract information from any invoice provided to you and return the output in the following JSON, right? And here let's define the JSON format, which is our schema dictionary, right? So for this, let's create an F string and then add the schema. Okay, we cannot directly add it, so import JSON. Because this is the dictionary, we want to do JSON.dumps of schema dictionary, right? And let's also add an instruction saying fill fields only when the information is available, just to make sure that the model is not returning the empty strings. Okay, so this is going to be our new prompt. Let's print the prompt. This is going to be our new prompt. Let's move to the next step where we load the model using VLLM. Now, we from VLLM import LLM, and our LLM object is going to be LLM of. Let's define the parameters. The first one is the model, which is going to be the model name. Let's copy this model URI from the Hugging Face, Wen 2.5 vision language 7 billion model. Paste it here, and we are going to specify a few more parameters to avoid the KV cache error. So one is max model length. This is going to be the 4096 tokens, and max sequence, max nominal sequence, number of sequence to process is 5. And we are also going to specify another parameter for the processor. So m processor quarks equals, okay, it's a dictionary, and it takes in 2 parameters. One is the min pixels, the minimum pixel, and we are going to set it to 784, which is 28 plus 28, and max pixel is going to be 1024 star 28 plus 28. Okay, and that's it. Let's run this code and see the model is getting good. Okay, now we have this model saved in the cache, and hence it should automatically pick it from the cache. Yes, now the model is getting loaded here. The checkpoints are getting loaded, and the model took around 15 GB of memory. And let's wait for the model to load successfully. Now we have this model object instantiated. Remember this particular step, we used the when class from transformers. Now that we use VLLM, if we want to test some other model, all we have to do is to just replace this URI with the. And of course, we are going to have few prompt template changes, but on this step, just the model. Okay, now let's go ahead with the next step. And now we have to set the output configuration. For that, we're going to import sampling params class, and sampling params will be sampling params of. We're going to specify a couple of parameters here. The first one is temperature, right, which is going to be 0.1, right? So the second parameter is max tokens, number of tokens to generate. Let's keep it as 1024 because we don't have a invoice where we have too many clutter text. And the third one is stop token IDs, the criteria for stopping. Let's keep it as none. So these are the parameters for output generation. Now let's go ahead and define our VLLM. VLM uses slightly different type of prompting style. To create VLLM prompt, let's define a function create VLLM messages. Given an image path in the prompt, this is the prompt we defined in the previous step. We are going to create a VLLM prompt, and which will have this placeholder, and this is the prompting style where we'll be defining a system message. It's optional. If you want, you can keep it. And then there's going to be a user message where we are going to have a placeholder for this image and the prompt, and then we are going to ask the assistant for the reply. Okay, and since we have this image, let's go ahead and load it. Image is equal to from PAL import image and do image.open of image path. Once the image is loaded and we have the prompt, we can define the VLLM input, which is going to be the first parameter is prompt. Is going to be the VLLM prompt, and this particular example takes multi-model inputs. And hence we have to provide the image as an input base. Okay, so this is the structure where we have the input, the base prompt, which is the prompt which we created in the using VLLM tags, and then the image. Here we are passing in the actual image loaded with PAL, right, and then do a return of inputs. Now let's try passing in one of the image. To do that, let's use create VLLM message and say test/test_0.png, and prompt is going to be the prompt which we created. Now here we can see we have the VLLM prompt ready for the inference. Okay, let's write some code for inference. To do that, let's iterate through the dataset for row in dataset of test. For every single row, let's use TQDM here to track the progress. TQDM. Okay. Now every single row contains the image as PNG and the ground truth, and we are going to separate this. The first step is to save the image. Okay. The image is going to be row of image, and this is in PNG format, and to save this we need to save it in a local path. So if not a os.path that exists, say tests folder, then let's create os.make directory of tests folder. Okay, now our image path is going to be os.path.join the tests folder, and the name of this image, which is going to be test underscore something dot png, and for the invoice ID, I'm creating a counter here, I equals 0, I equals 1 to create a unique ID. Now let's add I here. Now we have the image path, and we can directly save this image using image.save or image path. Okay, now we have saved the image. The next information that we have to save is the ground truth. For that, let's create ground list. Okay, now save the ground truth information. To save this, we are going to first gather the ground truth. Ground truth is going to be row of ground truth, which is a string, and hence let's do JSON.loads of this, and we are interested only on GT parts, and hence add GT parts here. Okay, so let's import JSON. Okay, now it's going to load this JSON and extract GT parse and return as a dictionary, and we can just append this information to the ground truth list. Okay, now we have the second step done, where we have saved the ground truth information. The third step is to create the LLM prompt. We have a method which takes two arguments. One is the image path, next one is the prompt. So use this method, create VLLM messages. So the message for this particular image will be create VLLM messages of image path will be the image path, and it also takes a prompt, which is the prompt which we created earlier, right? Now for every single image, we will have the message, and let's have a list bash messages equals a list, and append this particular message into the batch message. That's it. Now, ideally, if we are performing the batch inference, every whenever we meet the batch size, when this particular list is populated with the batch size, we have to process it. Since that we are using VLLM, we don't have to do it. We can process all 100 images in one shot. All we have to do is to create these messages and put it inside the list, which we have done now. Let's go ahead and run this. Let's run it for one message first to see if there are no errors. Okay, there were no errors. So let's go ahead and run it for the entire list. Okay, now it's going to run it for all 100. Let's wait for this to get completed. It took around 50 seconds to perform this initial step of creating the prompts and saving it inside the list. Now let's go ahead and do the predictions. So the predictions for us is going to be a single line statement, llm.generate. We have to pass in the list of messages that needs to be processed and the sampling parameters. If you remember, we created the output parameters here, which is sampling params. Let's just pass it to the LLM.generate. And that's it. Once we do this, we'll see that all the 100 inputs are 100 messages are batched, and these 100 messages will be processed in the concurrent fashion. Now the processing has already started, and we are able to see that in our previous step, we had sequential execution, and for every single image, we were waiting for 10 to 12 seconds. However, here the inference is way faster. Let's just wait for this inference to get completed. All the 100 images are processed successfully, and it took only 3 minutes and 52 seconds to process all the images. If we compare it against the sequential approach we did earlier, this approach is almost 4 times faster than the previous approach. There is only one part which is pending, which is nothing but the prediction outcome. So the type of predictions is a list, and this predictions contains not only the text output but also the text IDs. So we have to extract the text output from these predictions. To do that, we are going to create a list, prediction list. For each prediction, in the predictions, our result text is going to be the prediction of prediction dot outputs of 0, the text. And once we derive this result text, we just append it to the prediction list variable. And that's it. Now, once we run this, we have the prediction list. Let's take a random list to compare the outcome against the ground truth, just to make sure that we are processing the invoices in the correct order. Let's take the first outcome and let's compare it against ground truth list. And here we go. Here we see we are processing this in. As the VLM setup is way faster than the previous setup that we had, this enables us to test this invoice extraction experiment with different types of prompts and maybe different types of models as well. Now we have this prediction list and ground truth list as a list of strings. We can reuse majority of the code which we created earlier to post-process these output JSONs, and then the evaluation code which compares the prediction and the ground truth information computes the accuracy, precision, and okay, we can run the remaining set of code which is post-process, where we are converting this JSON information into a dictionary and appending it to the prediction list itself. Now the prediction list looks like this. Okay, now let's look into the accuracy part. In the evaluation, we have two steps. First one is the accuracy, and next one is the precision and recall. Now let's run the code for accuracy. Here we can see the invoice number, total number of keys, match keys, and overall accuracy. And the average accuracy for this prompt is around 48%. Maybe the reason being there are too many empty strings here, right? And the model was not able to capture the inputs very well. And let's go ahead and run the remaining part to make sure like everything is working. So this is the evaluation part where we derive the precision recall on F1 score. Let's run all this code, and here we go. We have the precision, recall, and the F1 score, and even we have the accuracy part. So overall, running this entire notebook, right from loading the data set till performing the evaluation, it hardly takes less than 4 to 5 minutes for us to complete benchmark. So we can test these with multiple prompts and multiple models and see how we can improve these results for the next steps.